Okay, welcome everyone to the Fields number 3 seminar. This is only the second talk in the seminar that we have. We just started the seminar last week. Michael Harris from Columbia gave a talk. Today we're very pleased to have Ritabrata Munshi from the Indian Statistical Institute, Kolkata. Ritabrata is a very well-known analytic number theorist, famous for his theorems on subconvexity bounds for various L-functions. He's joining us now from Calcutta, where I understand it's in the middle of a big storm. And it's also 10:30 in the evening for you. So Ritabrata, thanks for joining us for this. To the people listening, the audience, let me say that this seminar has a little bit different format because we want to make it as accessible as possible, especially to young researchers and students. So each speaker gives in advance of their seminar talk, gives a prep talk, which gives the background. So people can review that and become familiar a little bit with the ideas, and so that they can get more out of the actual talk. So I hope you've taken advantage of the talk that Ritabrata has posted. And so now maybe he will tell us about circle method and subconvexity. I suggest that we will handle questions at the end, and what you do is just put them in chat, and I will try to direct them to Ritabrata. If they're not too many, if it's not overwhelming, then I will just ask the person who's asking the question to pose it themselves, and then we can have a discussion on that. Good. Okay. Thanks, Ritabrata, please.
Okay, thank you. Thanks. So let me begin by thanking Kumar for his kind invitation and to Fields Institute for hosting this seminar series online. So I'm going to talk about the circle method and then application of the circle method to get subconvex bound for certain L functions. So in the first few slides, I'm going to run through some preliminaries about automorphic forms on GL2 and GL3. I'll talk about what they are, the L functions related to that, and some Voronoi summation formula, Kuznetsov formula. And next, I will move to describing what are called the Rankin-Selberg L-functions, which are convolutions of GL3 and GL2 modular forms. And then I will describe a new result about subconvexity about GL3 cross GL2 Rankin-Selberg L-functions. And finally, I'll give a complete proof of one such result. Okay, so let me start by telling you what, or recalling what GL2 forms are. So F is the Hecke modular form or mass forms. There are two different types of forms for GL2. One are holomorphic, they're called modular forms, and one real analytic, they're called mass forms. And so FZ, if it's holomorphic, then it will have a Fourier expansion like this. So it's n to the power k minus 1 by 2, lambda fn ENZ. And here EZ for us is e to the power 2 pi IZ. This is the standard notation for analytic number theories. And if F is a mass form with spectral parameter tau, then it will have a Fourier expansion which will look like this, where here K is a Bessel function, the K Bessel function. Okay. Okay, Z here is x plus Iy is a point in the upper half plane. So the mass forms and modular forms are functions on the upper half plane satisfying certain transformation property with respect to some discrete subgroup of SL2Z. And so I'm normalized lambda Fn in such a way, this expansions in such a way that the lambda Fn's which are now Hecke normalized Fourier coefficients, so that the value of lambda F at 1 is 1. And so these are Hecke forms. So with respect to the Hecke operator Tn, Tnf is lambda Fn times F. So lambda Fn are the Hecke eigenvalues for the nth Hecke operator. And says that the Ramanujan bound in this case will be that lambda Fn is bounded by n to the power epsilon. So for modular form, it is known that this holds. This is the work due to Delin. And for mass forms, you expect such a bound, though it's not really known so far. Right, so what is this spectral parameter tau? So for mass form, this is delta is the Laplacian on the upper half plane. So delta F is 1 quarter plus tau square F. So 1 quarter plus tau square is the eigenvalue for the Laplacian. So if when F is a mass form, it's actually Hecke mass form, then it's eigenfunctions of all the Hecke operators and also the Laplacian operator. Right? Now, given such a modular form or mass form, we associate an L function to it, and that's defined by this Dirichlet series. So you take those normalized Fourier coefficient lambda fn and divide by n to the power s summed over n. So it's the standard Dirichlet series. And so as we are assuming that lambda fn's are Hecke eigen values, if f is a Hecke eigen form, there are some multiplicativity conditions on lambda fn, and the Dirichlet series is also given by this Euler product. Okay, and it's a, you can see it's a degree 2 Euler product. So the psi over here is the Nibben-Tippus of f. So right, and then we can factorize this degree 2 Euler factor into 2 linear factors, and we get these local parameters alpha f1 and alpha f2. Okay, so LSF, the L function, has an integral representation. So it can be written as a Mellin integral of the actual form f. And from this, we can derive that this L function is entire. So it has an analytic continuation to all of C without any pole. And it satisfies a functional equation, which looks like this. So if you multiply LSF with a suitable gamma factor, which looks like this, when f is holomorphic and k is the weight of the form f, or if f is mass, then the gamma factor looks like this, where delta over here is 0 and 1 depending on whether the mass form you're looking at is even mass form or odd mass form. And then if you complete the L function by multiplying this by the suitable gamma factor, and here n is the level of the form, and you multiply by n to the power s by 2, then this completed L function is related, the value of this at s is related to the value of the dual form f bar at 1 minus s. Okay, and then this epsilon f is what's called the root number, is the sign of the functional equation. So absolute value of that is 1, and for n square free, actually you can write it down explicitly. And for holomorphic forms, it looks like this. So it's I to the power minus k, where k is the weight, the conjugate of the nth normalized Fourier coefficient for f, and g psi is the Gauss sum for the Nibben-Tippus by square root of n. Okay, so this has absolute value 1, okay, for n square free. Right. For this Fourier coefficients, we have what's called the Voronoi summation formula. And I'm writing the Voronoi summation formula for the simplest case. So this has the Fourier coefficient lambda fn and the additive character en by q. In the simplest case, we assume that this denominator q of the additive character is divisible by the level of the form n. So n divides q. If n divides q, then the Voronoi summation formula says that this sum over here is equal to this sum. Okay, so here g is going to be a nice function. We can think of it as a bump function supported between capital N and twice n. And on this side, you have this a n gets transformed into minus a bar n, where a bar is the multiplicative inverse of a modulo q. So I'm assuming that a and q are co-prime, so this fraction over here is reduced. And on this side, we have the Hankel transform of the function g. Okay, so jk minus 1 is the Bessel function, j Bessel function of order k minus 1. Okay, and we have such formula even in the case where n does not divide q. Then it looks a little complicated in that case. There are certain situations where we may not have such a nice formula. For example, if if n is a square and a part of say if n is p squared and p divides q, but p squared doesn't divide q, then the formula is not really that clear, and it's not clear. And also such a formula. So I'm writing this down for modular form. This k over here is the weight of the modular form, but such a formula is also there for mass forms. Okay, I'm not going to write it down explicitly here. Okay, so this is a summation formula for the Fourier coefficients of a holomorphic form. And there is another summation formula that I want to recall over here, is that, so here I'm summing over n, the form is fixed. And here I have two Fourier coefficients, lambda fn and lambda fm of the same form f. The n and m are fixed. These are two positive integers which are fixed. The form is varying. And here I'm taking the space of is a basis, a Hecke basis of modular forms of level n, Leibniz psi, and weight k. And WF inverse is what's called the spectral parameter. So it will basically have, it's more or less like 1 by the Peterson norm of the form F. And then this average is equal to delta of n minus m and plus this side. And here J is again the J Bessel function that we had in the Voronoi formula over here. And now we have this sum over here, which is the Klosterman sum, SIMNCN. And the delta is the Kronecker delta function. So delta of any integer is either 0 or 1. Delta of 0 is 1, and it is 0 for all non-zero integer m. Okay. So if you closely look at this, then you will see that here 1 by omega f or 1 by wf is of size 1 by kn. And as we have normalized the Fourier coefficients, these lambda fn and lambda fn are more or less like 1. So on the left-hand side, you have a sum like this. The size of these things over here are 1 by kn, roughly speaking. And on this side, you have the Klosterman sum. The word bound for the Klosterman sum is square root of Cn. And then you have Cn over here. And the size of the Bessel function is like 1 by square root of the order k. And so if I look at the block where small c is like capital C, so small c is between capital C and twice capital C, then this is the size of the terms that I have here. And if I sum over C, then I get square root of C by square root of nk. So now, so this part, your number of f is also like k times n. So this is like 1. And this part is like square root of C by square root of nk. Okay. So a sum of length nk, because that is the number of forms that you had, is the saving that I have is from 1, it goes to this. So the saving is square root of nk by square root of C. And so that is same thing as the square root of the initial length by the square root of the final length. So that's something I wanted to recall over here. If you have looked at my prep talk, I've stressed on the fact that whenever you have a summation formula like this, the saving that you get, by saving I mean that if I estimate the left-hand side trivially and the right-hand side trivially, the ratio of the size of the left-hand side by the size of the right-hand side is the saving that I get from the summation formula. And it's always going to be the square root of the initial length by square root of the final length. Okay, that's true for Voronoi summation formula. That's true even for the Peterson trace formula. Okay. All right, so now let me move towards mass forms. And as we all know that mass forms are more mysterious, and but there is a Weil law which guarantees the existence of mass forms. And the Weil law says that if I'm looking at for mass forms of level n, and if I take the spectral parameter between capital T and capital T plus 1, then there are roughly capital N times capital T many mass forms with spectral parameter between T and T plus 1. So that is the same thing as saying over here that there's k times n, roughly k times n many forms in this space. Okay, it's the size of the basis of the space of all cusp forms of level n, Leibniz psi, and weight k. So that nk and nt, nt is the analog of that nk. Okay, and so here also, I've also already mentioned that there is an analog of Voronoi summation formula, and there is also an analog of the Kuznetsov trace formula in this case, and the Peterson trace formula. It's called the Kuznetsov trace formula, and it's slightly complicated. as you can see, that you have here, so these are the spectral weights now. And again, we have the Fourier coefficients. Now we have an extra contribution coming from the non-holomorphic Eisenstein series over here. And then I have this diagonal term again, the Kronecker delta function times h. H is some sort of, taking care of the mass coming from the function h. So h is up to you to choose. If you choose any reasonable function satisfying certain conditions, then you have such a formula. And again, we have this closed Riemann sums, and instead of the Bessel function, we have some integral transform of the Bessel function. So this is an analog of the Peterson formula, slightly more complicated. Again, if you want to see what this formula is doing, the saving that you get is again square root of the initial length by square root of the final length. The formula is dissolving the Fourier coefficients and giving you a delta symbol, which is the diagonal contribution, and closed Riemann sums. So it's basically reducing from a GL2 harmonic to a GL1 harmonic. All right. So now let's move to GL3 mass forms, which are much more complicated, and so complicated that I'll not be able to write them down explicitly. So I'm just going to say that, okay, so for simplicity, I'm going to stick to level 1. So I'm looking at Hecke mass forms for SL3Z only, and not congruent subgroups of SL3Z. And they have a Whittaker Fourier expansion, which looks like this. So these are the Whittaker Fourier coefficients of the form capital F. And times there will be, like in the case of GL2, we had a K-Bessel function, or here we'll have an analog of the K-Bessel function that's called the Jacquet-Whittaker function. It's slightly complicated, so I'm not going to write it down. But what I want to write, so now what is Z? Z is not on the upper half plane anymore. So Z is something in GL3R by O3R R cross. Okay, so this is the orthogonal group, and this is the 3 by 3 real invertible matrices. So if you replace 3 by 2 here, then you get the upper half plane. So this is the generalization of the upper half plane. Okay, and here the lambda Fn are the Hecke normalized Fourier coefficients. And again, it means that lambda F11 is 1, and lambda Fm1 is the eigenvalue for the Hecke operator Tm. Also, we have the associated L function, which is again given by a Dirichlet series, which looks like this. Now lambda F1n by n to the power s. So you fix one of them to be just one coefficient to be just 1. So m is equal to 1. And now again, we have the Hecke relations, which reduces this Dirichlet series to an Euler product, which is now of degree 3, because it's coming from GL3. So it's a degree 3 Euler product. And the thing is that for a real part of S greater than 1, both the Dirichlet series and the Euler product converge absolutely. And again, I can factorize this degree 3 Euler factor into 3 linear factors. And I'm going to call the local parameters as alpha F1, alpha F2, and alpha F3. Okay. And again, there is an integral representation of this L function, and that will give the analytic continuation of this L function to all of C. There are no poles, and again, and one can show that it satisfies the functional equation, which looks like this. Okay. So now again, you have to multiply the L function with a suitable gamma factor. And I'm taking the level to be 1, so there is no n to the power s by 2 term over here. So let me just mention what these alpha j's are. These are the spectral parameters of the form F. So they are called the Langlands parameters. And if you multiply L with this suitable gamma factor, then the value of this completed L function at S is related to the value of the conjugate form at the point 1 minus s. Okay, so that's a functional equation. And again, we have a Voronoi summation formula for degree GL3. And again, as you can expect, it's much more complicated. So it looks like this. Again, we have an additive character over here and a smooth, nice function over here. G, A, and Q are co-prime. And now this sum gets transformed into something like this, where this additive character becomes a Klosterman sum. So that's something new, because in case of GL2, the additive character was going to another additive character, with A being replaced by the multiplicative inverse. But here it's going to the Klosterman sum. Okay? And A is replaced by A bar. Okay? And then you have AN cubed by N. Okay? And then again, we have an integral transform. There are 2 copies of them. And that also is quite complicated to explain. So it is given by an inverse Mellin transform, which of a function which involves the Mellin transform of the weight function G multiplied by a suitable gamma function, gamma plus minus S, where here again you can see the Langland parameters appearing here. So again, if you look at this formula, and if you try to analyze this, you'll see that the saving that you are getting is again square root of the initial length by square root of final length. Okay, so so the conductor of this part, so if you want to see how complicated this sum is on this side, then there are 2 things that are contributing to the complication. One is this Q, the denominator of the rational fraction over here. And the other thing is the spectral parameter. Okay, so larger is the spectral parameter, more complicated is the form. And, since it's a GL3, the Q over here gets cubed. So it's Q cubed times the product of the spectral parameters. So this is the conductor of this sum over here. And if you look at it, so if the initial length is, say, capital N, then the dual length, so if you look at, if you study the integral transform, you'll see that this part of the sum is actually supported in with m n square near the conductor, which is this, by the initial length. Okay? And then if you analyze the size of the integral transform and use the well bound for the Klosterman sum, you will see that this formula is actually saving square root of the initial length by square root of the final length. Okay? And also there is a version for GL3 Kuznetsov-Dress formula, and I'm not going to write it down, but if you look at the work of Blomer and Burtkin, you can learn a lot there. Anyway, so let me now look at the L functions that we are interested in. So these are the Rankin-Selberg convolution of a GL2 form, f, small f, and a GL3 form, capital F. Okay. By definition, the L function is given by this Euler product. So alpha f1 and alpha f2 are the Euler, the local factors for the form small f. And these alphas are the local factors of capital F. Okay, and there are 2 of them, 2 of this and 3 of this. And so there are like 6 factors, linear factors over here. So this L function is actually an L function of degree 6. Okay, and if you expand this Euler product, which converges absolutely again for sigma or the real part of S greater than 1, then in that half plane, it's given by this Dirichlet series. Okay, so these are the normalized Fourier coefficients of the GL3 form, the normalized Fourier coefficient of the GL2 form F. Psi was the Nibin-Tipis of the form small f. Okay. Again, we can have an integral representation of this form, which looks like this. So you have to just embed the SL2Z in the top left corner of SL3G, and then here, that's the iota Z, and then you have to multiply by a suitable y to the power s minus 1, and then integrate this. It's kind of a Mellin transform, and then you get this L function over there. Okay. And from this, you can get the analytic continuation and the functional equation. So, and a deep result of Kim and Shahidi says that these L functions are actually automorphic. So they correspond to certain automorphic representation of GL6. All right. So now the main problem, the subconvexity problem, is about understanding the size of these L functions. Okay. And as you know that it's enough to understand the size of the L function on the central line. That's the line passing through the real part 1/2. So I'm going to take the S to be 1/2 plus ID now. And I want to look at this L value, right? And now I want to see how large this is as T varies, or when the parameters of F vary, or the spectral parameters of capital F vary. Okay, so there are three different aspects that we are interested in. So, for example, we can keep the small f and capital F fixed, and then I can take T high up on the central line and try to understand how the size of this is varying with as T goes to infinity. And that will be, so there I will be trying to get a bound in terms of T. So that will be the T aspect bound. Or we can take T to be something fixed at T equals to 0, the central point, and we can fix the GL3 form and vary the weight and the level of the GL2 form and try to find out how this varies with that. Or we can fix the GL2 form and just fix at the central point and vary the spectral parameters of the Langland parameters for capital F and see how this is growing with that. Okay? And from the functional equation and the usual convexity principle of complex analysis, we can show that if small f and capital F are kept fixed and T is varying, then this L function grows like T to the power 3 by 2. Okay? So that is because this is a degree 6 L function. So if you look at the functional equation, the gamma factor has 6 gamma functions in there, and each of them will involve a T. So the conductor becomes T to the power 6. Okay, and T to the power 3 by 2 is actually 1/4 of T to the power 6. T to the power 6 to 1/4 is T to the power 3. So this is the convexity bound. Okay. And if I fix T and capital F, then K to the power 6 n cubed is the conductor of the function, and the 1/4 of that is the convexity bound. And if I fix T and small f, then there are 3 spectral parameters coming from F, but since there are 6 gamma factors, each of the spectral parameter gets doubled. So it appears in 2 gamma factors, each of them. And so the conductor becomes this product square, and 1/4 of that is convexity bound. So in particular, if all the alpha j's are of size, say, capital T, then you'll have T square 3 times, so T to the power 6, and 1/4 of that. So that will be capital T to the power 3 by 2. Okay? Okay, and the subconvexity problem is about improving this exponent. Okay? All right. So why do you expect to improve the exponent? Of course, we have the Grande Riemann hypothesis, which says that all the zeros of those L functions lie on the central line, and that implies the generalized Lindelof hypothesis, which says that the exponent here can be taken as arbitrarily small. That means you can actually drop this 3 by 2 altogether, and the bound should be T to the power epsilon for epsilon arbitrarily small. Or you can drop this 1/4 over here. So that's the Lindelof hypothesis, and we are far from proving that. But also a good thing about this L function is the following. So if I replace the capital F by the, say, the Eisenstein series, I think it's a minimal parabolic Eisenstein series, then this L function is almost like the cube of the GL2 L function. Okay, and if I replace the GL2 form by an Eisenstein series, then this is like the square of the GL2 form. So if I get a bound for these L functions, and if the bound is actually not sensitive to the forms being cuspidal or not, then we can get good bounds for the GL2 and GL3 L functions in one stroke. So it follows that if we get subconvex bounds here, we can get subconvex bounds for GL2 and GL3 in one stroke, right? And that's one good thing about looking at the GL3 cross GL2 Rankin-Selberg convolution. And another reason for looking at this convolution is that they appear in Watson formula, which relates the period integrals that appear in the QEE problem to this type of L function, LS F sim square phi, where phi is a GL2 form, and sim square phi is then a GL3 form. So it's actually a GL2 plus GL3 Rankin-Selberg distribution. So that's one of the big motivation to study the subconvexity problem for such L functions. Okay, so the moment method has been used to get subconvex bounds in this case. So let me fix an orthogonal basis, Hecke basis for the space of mass forms for SL2Z. We know it's discrete, the spectrum is discrete, so FZ is giving you an enumeration of that. And so there's this result from Lee, it's very well known, that if you take a self-dual GL3 form, and if I take the parameter m to lie between t to the power 3 by 8 and t to the power 1/2, then this sum over here, so this is the GL3 plus GL2 L function, and here the spectral parameter of the GL2 part is ranging between t minus m and t plus m, and this is the integral of the GL3 form, L function of the GL3 form square. Then this is bounded by t times m, so it's actually t to the power 1 plus epsilon times m, but I'm going to write it as t times m, roughly it's t times m. And why is this useful? Okay, there's a deep result of Lapid which says that these L values are non-negative if you take capital F to be self-dual. So if capital F is a symmetric square leaf from a GL2 form, then this L values are non-negative at the center. And if you have that information, then here you are adding all non-negative numbers. And so if you have an upper bound for this sum, then from that upper bound, you can get upper bound for the individual terms appearing over here. Okay? That's the moment method. Okay? And from this, Lee derived subconvex bounds for this GL3 cross GL2L function. So this is in terms of the spectral parameter of the GL2 form. Okay? So this is the convexity bound would have been 13 by 8 or 3 by 2, and she got 11 by 8. So it's 1 by 8 better than the convexity bound. But she had to take capital F to be symmetric square lived, because otherwise you don't have this non-negativity, and then there is nothing you can derive from this such an inequality, right? And also she got the T aspect subconvexity for the GL for the symmetric square. Okay, so again here 12 by 16 will be the convexity bound, and she got 11 by 16. Okay, and then there was a subsequent work of Blomer, where he looked at the twists of the symmetric square by quadratic form and quadratic characters. And again, for quadratic character, we have such a non-negativity result. And so using that, he could also derive subconvex bound for symmetric square twisted by quadratic character. Okay, but both Xiaoqing Li's and Blomer's result actually are inspired by a well-known result of Andre Vanich, where they look at this third moment of degree 2L function. Okay, so here FJs are again the Hecke basis, and here they were taking chi to be a quadratic character, and here they have a cubic moment, and they get such a bound. And from this, since again you have non-negativity for these terms, here anyway you get absolute value, so it's no problem. But you have non-negativity for this. From that, they could derive like this subconvex bound, very strong subconvex bound for quadratic twists of GL2 forms. Okay. And the main ingredients in these results are the Kuznetsov-Press formula and the Voronoi summation formula. Okay, and but so as I mentioned that you need to stick to symmetric square to have non-negativity of the central value. But once you go to non-self-dual, there are no non-negativity results. You do not expect them to be non-negative. So such a computation of first moment will not help you give anything about the bounds for individual functions. So in that direction, Matthew Young looked at the second moment. So he's taking absolute value squared. So now they're all non-negative. And he computed the second moment over some family. So here the spectral parameter of Fj are varying between t and 2t, and it's integrated from minus t to t. And he could prove that this is bounded by t to the power 3. So you'll see that this is because the number of forms you have here is like t square. So it's there are t cubed many points of summation over here. So it's kind of proving the is Lindelof on average. And from this, you can derive the convexity bound for the individual function, but you'll not get any subconvex bound. Okay? And to get subconvex bound, one either needs to get an asymptotic formula here, or needs to shorten this integral to something shorter than length t, okay? Which is still open. Okay, so now I come to the result that I proved a couple of years back. So here, so small f is a SL2Z form, capital F is an SL3Z form. Capital F need not be self-dual, so it can be any generic SL3Z mass form. Small f, I'm sticking to SL2Z for simplicity, but you can take it to be of any level. But I'm interested in proving subconvexity in the t aspect. Okay, so again, the convexity was t to the power 3 by 2, and I could put 3 by 2 minus 1 by 42. So that was the saving over convexity. Okay. So the proof is, the approach is slightly different. So we are not trying to compute moment. Okay? So actually computing moment is a more difficult job than proving subconvexity. So, and as we'll see, I'll give a complete proof of how to derive this bound. But once you have a subconvex bound this type, now replacing small f or capital F or both by Eisenstein series, you can get subconvex bounds for degree 1 L function. This is the Dirichlet L function, degree 2 L function, or degree 3 L function. So you get t aspect subconvexity for degree 1, degree 2, degree 3, and degree 6, GL2 plus GL3 function in one stroke. Okay? Of course, the bounds here are not as strong as you can prove in using other methods. Okay, so now let me try to give a proof of this of the theorem. Okay, so first we want to estimate this on the central line, and there is one method from classical analytic number theory. It's called using the functional equation. You can we have something called the approximate functional equation, which gives you an expression for this L value inside the critical strip. And then if you suitably truncate the approximate functional equation, then you can get an inequality of this type. Okay? So here, this L value it can be bounded by a sum Sn by square root of n, where the length of the sum n, the length n is going up to t to the power 3. Okay? So what is t to the power 3? T to the power 3 is the square root of the conductor of this. Okay? So t appearing in 6 gamma factor, t to the power 6 is the conductor, so t to the power 3. Okay? And you have an arbitrarily small error term over here. If you want, you can replace it by minus 2020. I put it down last year, so it's 2019 over here. Anyway, and what is Sn? Sn's are sums of this type. So it involves the Fourier coefficients of capital F, the Fourier coefficient of small f, and then there's a smooth weight, and you have this nr squared to the power it. Okay? And you will notice that if you put the trivial bound over here, if you use the Ramanujan bound on average, then you recover the convexity bound. Okay? So to get a subconvex bound, what you need is to prove some cancellation in this sum. Okay? And let me just drop the r over here, and because it's not, r comes with a square, so it's not really
the main part. The main part is the n sum. So I'm looking at the n sum. It's lambda fn1, lambda fn n to the power it. Okay? And n is of size tq. And I want to show that there is cancellation over here without computing moment. So this is what I do. So I want to introduce the circle method to separate the oscillation of the Fourier coefficient of GL3 and the Fourier coefficient of GL2 clubbed with m to the power it. So I write Sn in this way, where again delta n minus m is the Kronecker symbol. This is 1 when n equals to m and 0 otherwise. So that's trivial. And now I want to introduce an extra integral over here. It's not really necessary, but from a psychological point of view, it helps. So I'm introducing this integral. Okay, and I have n to the power iv and m to the power minus iv, and since n equals to m, so this integral is actually gives you k. Okay, so I'm assuming that the whole mass of w is 1. So that balances this k. Okay, and then I want to replace this Kronecker symbol by a Fourier expansion. Okay, this is the circle method part. Okay, and the circle method that I'm going to use is called the delta method, which says that delta n has such a Fourier expansion where capital Q can be chosen as anything non-negative and or positive, and then h is certain function which is reasonably nice if you pick capital Q to be large enough. Okay, so basically it means that if you have a priori information that small n is lying between minus capital N to plus capital N, then you pick capital Q to be square root of the size of square root of capital N. Okay, so that's the size of the equation. And then this h is not really oscillating that much. So you can think of h as basically 1. Okay, so that's what I'm going to do. Okay, I'm going to pick my q in a reasonable way. Okay, so this is a circle method without minor r. Okay, so now I'm going to pick my q to be square root of n by square root of k. Okay, the reason is okay, so now this is why I introduced the integral. So the integral over here is, if you forget that n equals to m over here, if you just look at the integral of n minus m to the power iv, then this says that this integral will be negligibly small unless n minus m is bounded by capital N by capital K. Okay. So saying that small n minus small m equals to 0 is actually you're trying to detect an equation of size capital N by capital K. Okay. So yeah, so I pick my the size of the modulus in the circle method to be square root of the size of the equation, which is now capital square root of n by square root of k. Okay. All right. So now I've replaced this expansion of delta over here, and that will separate the n from m, and I arrive at this expression. Okay, so now the GL3 part is nicely separated from the GL2 part. Okay, and these are the summation points coming from the circle method, and this is the integral. And now if you estimate this part trivially, then so this is bounded by capital N, this m sum is bounded by capital N, and the number of points of summation here is q square, and this is the integral of size k. So kq square is balancing the number of points of summation that we've introduced. And this is n and n, so it's trivially bounded by n square. And we need to save n because we want to show that Sn is smaller than size n. So we want to save n and a little bit more, t to the power theta for some theta positive. Okay? And that will give you a subconvex bond. Okay? So now since n and m are separated, I can apply the Voronoi summation formula to the n sum. I can apply the Voronoi summation GL2 Voronoi summation formula to the m sum. Okay, and this is what we are going to get. So if I apply the GL3 Voronoi summation formula, so I can recall that the additive character over here was becoming a Klosterman sum. So it is S of minus A bar NQ. And then I had integral transform. This integral transform will involve the oscillatory part into the power IV. Okay. And now if you want to find out what will be the dual length, the dual length will be the conductor of this sum by the initial length. The conductor is Q cubed, the size of V was K, Q cubed, K cubed, right? And capital F is fixed, right? And if and Q was root n by root K, so the conductor is capital N, capital K to the power 3 by 2 divided by N. So this is the dual length. Okay? And the saving is square root of the initial length by the square root of the final length, and that turns out to be n to the power 1/4 by k to the power 3/4. Okay, and then the Voronoi transform formula for GL2 transfers this sum into this sum over here. So A now becomes A bar, and again now the conductor is T square times Q square. Small f is fixed, and that divided by capital N gives you T squared by capital K. Okay, and if you save nk to the power 1/2 by T, so that's the amount you are saving from the GL3 and the GL2 Voronoi summation formula. And now this is the magic that makes everything happen over here. So now if you collect the Klosterman sum over here and the additive character over here, and do the A sum was coming from the circle method, then this magically reduces to an additive character. So it becomes E of minus M bar N by Q. Okay. So this in one hand gives you a square root of Q saving, because this is a character sum and you get a square root of Q saving. Trivially, it's root Q times Q, it's Q to the power 3 by 2. Now it's Q, so you have a square root of Q saving. And the character sum dissolves and gives you a nice additive character. Okay. And moreover, you save square root of K if you do the integral over V. All right. So now if you're keeping the account, then here you have saved this much, here you have saved this much, and now you have saved square root of Q and square root of K. If you put them everything together and recall that you wanted to save N and something extra, now it remains to save T and something extra after all this work. And the sum that you ultimately are getting over here looks like this. So we have the Q sum from the circle method. This is the dual N sum, the dual M sum, and there is some integral transform which will be oscillating like K. Right? So that we need to save T. So now the next step is we apply the Cauchy-Schwarz inequality or Cauchy's inequality. And using the Cauchy inequality, I'm getting rid of the GL3 Fourier coefficient. So I'm taking the GL3 sum outside. The Fourier coefficient is gone. You have to use the Ramanujan bound on average for GL3. Put the Q sum and the GL2 sum inside. Okay, absolute value. And before the Cauchy, we wanted to save T. So after Cauchy, we want to save T squared. And so now we open the absolute value square and apply Poisson on the N sum, right? And you, so there will be two parts. So there will be a diagonal part and the off diagonal part. In the diagonal part, you'll be saving the number of frequencies that you have inside the absolute value square, and that is QT squared by K. And you need this to be larger than T squared. That will mean that Q has to be larger than K. And that is same thing as having this. And on the other hand, you also want off diagonal to be defined. Off diagonal will be by Poisson, as I said, that its saving is the initial length by the square root of the conductor. So this is the initial length by square root of conductor. But you have you magically save more because you have an additive character over here. Okay, so the additive character gives rise to a congruence. And that will mean that you save the whole Q and not the square root of Q. Okay, so the saving that you get is the initial length by the square root of the conductor part is the analytic conductor, which is K was the analytic conductor, and so it's the square root of K. Okay? And this is larger than t squared if you take k to be square root of t, right? So that's yeah. So if k is picked between t and square root of t, you get a subconvex bound, and picking optimally the size of k, you get the bound given in the statement of the theorem, right? And now this method also gives you other results for GL3 cross GL2 L function. So there is a recent preprint in the archive by my student Prahlad Sharma, and he looks at the GL1 twist of GL3 cross GL2 Rankin-Selberg, and he proves a subconvex bound. Again, p to the power so chi is a primitive character modulo p, assume p to be prime for simplicity, and get p to the power 3 by 2 minus this much saving. And then there is my other student is working on this problem, and he's still writing it down. So he's looking at the spectral parameter. So capital F is fixed and small f is varying, and the spectral, so suppose small f is a modular form of weight k, then k to the power 3 by 2 is the convexity bound, and he's getting something like k to the power 3 by 2 minus delta for some delta positive. Okay, so this is, so recall that Lee's famous result gives such a subconvex bound where capital F is self-wall or symmetric square lift of a GL2 form, but Kumar's result will be true for any GL3 form, not necessarily self-wall. There is another work due to Kumar and Malesham and Singh, and where they fix the small f and vary capital F. So if capital F has spectral parameters alpha j's of size t, and suppose they're in a generic position, so alpha 1 and alpha 2 are not near each other, alpha 2 and alpha 3 are not near, and all of them are of same size, capital T. And then you have to, so if you assume, so it's a conditional result, so you have to assume that the Fourier coefficients are not that small, that often, then you get a subconvex bound. Okay, and they can get a unconditional subconvex bound if they assume that two of the alphas are near each other. So their result is conditional in the generic case and unconditional when the spectral parameters are near the walls of the Weyl chambers. Yeah, so I was just saying that, you know, here it was the GL2 form is fixed and you're varying the GL3 form. Mm-hmm. And you get a subconvex bound in the spectral parameters for GL3. If you assume this condition on the Fourier coefficients are not that small, okay? Mm-hmm. When the spectral parameters are in the generic position. But if you assume that they are not generic, if you assume they say alpha 1 and alpha 2 are near, right? Mm-hmm. So the distance between alpha and alpha 2 say is smaller than t to the power 1 minus theta, then you have saving. You do not need this condition and you get a subconvex bound. Mm-hmm. And so this nicely complements the result of Blomer and Butkin, where they get a subconvexity bound for GL3, but when they're in the generic position.